Okay, you can play with constants. Okay. Another thing we can do is we can differentiate or integrate. So there's the theorem is, I won't put it on the board because it will take up the whole board, but that's one reason we want to play with this is because it's really easy to differentiate a polynomial. Okay. And the theorem says that whenever you differentiate a power series, you maintain the radius of convergence. Okay. Your interval of convergence may change. If you've got convergence at endpoints, you may lose it when you differentiate or integrate. Okay. So be aware of that, but your radius stays the same. Okay. So for example, let's stay with this same function. What's the derivative of 1 over 1 minus x? Okay, let's think about that. So 1 over 1 minus x, what's its derivative? Right, so I could use the quotient rule, or I could think of this as 1 minus x to the minus 1 and use the chain rule. Right? Should put square brackets there until I differentiate. So if I use the power rule and the chain rule here, this will be minus 1, 1 minus x to the minus 2, times the derivative of 1 minus x, which is another minus 1. So we just get 1 minus x to the minus 2, which is 1 over 1 minus x squared. Quantity squared, right? So that's what I get when I differentiate this. What if I differentiate this long polynomial? Think about the derivative infinitely long. It's not a polynomial, I call it that, but polynomials are always finite, so that's the difference. But we're going to treat it like it's a polynomial. So what's the derivative of this? Well, the derivative of 1 is 0, the derivative of x is 1, derivative of 2x squared is 2x, derivative of x cubed is 3x squared, 4x cubed, etc. All right. So this tells me that, I can drop that 0. This tells me that this series should add up to 1 over 1 minus x quantity squared, at least on the interval minus 1 to 1. Okay. I should go back and check each of those endpoints, but I'll still get divergence there. Right? But we like to have nice short forms for our power series. So think about differentiating this. Just do the terms. The nice thing about differentiating is the derivative of a sum is the sum of the derivatives. So I can move the derivative in on the terms of the sum, swap the sum and the terms, and the derivative. The derivative of x to the n is easy enough, that's nx to the n minus 1. So there's a nice closed form. Notice if you plug in 0, you get 0. Plug in 1, you get 1x to the 0. Plug in 2, you get 2x to the first. Plug in 3, you get 3x squared. Okay. So that is this series written that way. But another way, we could re-index, because we like to have our powers on x to be the index, the thing that we're summing over. So if I index, and this can be tricky, so I'm going to have x to the n. So when n is 0, oh, wait, this doesn't start at 0. This starts at 1. Right? Because otherwise I'd have, that's that 0 term, and I don't want to x to the minus 1 power. So this starts when n is 1 with that term. Okay? 1x to the 0. Okay? So if I want to go up a power on n, on my there, well, I've replaced n minus 1 with n, so this n becomes an n plus 1. I went up 1 on the n, right? And for that to match this, I'm going to start at n equal to 0. Because I went up 1 on the end. When I started at 1, I now start at 0. Okay. So notice when n is 0, I get 1x to the 0. When n is 1, I get 2x to the first, etc. Okay. So that's a way to get a power series for 1 over 1 minus x squared. Let me put that right in here. So 1 over 1 minus x squared, 1 minus x quantity squared, is the sum n equals 0 to infinity of n plus 1 x to the n. Okay. Centered at 0. Radius of convergence is 1, then you would need to check the endpoints, -1 and 1. Clearly, they're both going to diverge. Okay. So this is only valid for x in the interval -1 to 1. Okay. So some things that come out of that. Until now, let's pick a value of x that's in that interval. Say I pick x equal to -1/2. Okay. So this would be 1 over, I'd have the sum n equals 0 to infinity of n plus 1 times -1/2 to the n. Okay. Or I would get, let's see, 1, when n is 1, I get 2 times -1/2. When n is 3, I get, or when n is 2, I get 3 times -1/2 cubed squared. When n is 2. When n is 3, I get 4 times -1/2 cubed. Okay. Notice this is not a geometric series because my coefficients are getting larger and larger. Until now, you could have tested this series to see it converge, but you wouldn't know what it converged to. But now we know that it converges because -1/2 is in this interval, and it converges to 1 over 1 minus -1/2, which is 1 plus 1/2 squared. But that's 3/2 squared, which is 9/4. 1 over 9/4 is 4/9. If you add all these up to infinity, it'll add up to 4/9. Okay. Pretty cool, isn't it? So that's differentiating. Same thing works with integrating. Let's take the same series. I'll erase this guy. 1 over 1 minus x. And let's integrate it. What's the integral of 1 over 1 minus x? This is one where you do a u substitution, right? Let u equal 1 minus x. du is negative dx. So dx is negative du. That's my u. Factor the negative out. This is negative natural log absolute value of u plus c, or negative natural log absolute value of 1 minus x. Okay. So that's what this function integrates to. What's the polynomial integrate to? Well, the integral of the sum n equals 0 to infinity of x to the n dx. Well,